Hello there. This is my first lecture on logarithmic amplifiers. And logarithmic amplifiers are fascinating circuits. It's nice to have a circuit that can do mathematical operations. It can multiply or it can divide, find the root square, find the logarithmic value of an input. So these circuits are really fascinating. I'm going to talk about a simple circuit today. That circuit gives you the logarithmic of Vn. So whatever you put as Vn, it will find the logarithmic for it and present it as the output. So for example, if you're having 10 volts as an input voltage, you have an output voltage of -1. Plus 10 volts gives you a -1. That's the logarithmic because that log is to the base of 10. And you can set it, by the way, to any log that you want. But the one in here, based on this amplifier, non-inverting amplifier, is to the base of 10. So what this circuit is made of? This circuit is made of, let's say, this inverting amplifier, and a non-inverting amplifier. Here, you have a matched transistor pairs. You have a protection diode in here to protect that transistor from reverse voltage between the emitter and the base. You have a decoupling cap in there for higher frequencies or whatever, because you have a current generating device in here, which is a Q1. So this is our circuits. Resistors to set the feedback, resistor in here to set the current, and we have a current source in here, which can be replaced by a resistor, by the way. But the idea that you have to have about 1 milliamp going through that resistor. So you can set your voltage in here to whatever value you want. The idea that you have to have around 1 milliamp of current, because what we are talking in here is just a fluctuation of very, very limited voltage between the VBEs. Okay, now in order to understand this circuit, and we have very complicated circuits later on, especially that RMS detectors and the ones that find the root squares and things like that. But we're going to start with a simple circuit like this one in here. We have to go to the basics. I believe I made about 15 or 20 lectures on bipolar transistors so far. So we'll go back just a little bit and waste about a minute in just discussing the behavior or how a bipolar transistor behaves when a voltage is present between the VBE and the relationship of that to the IC. Okay, here we are. I'm interested in this. This is the base for our lectures from now on, or logarithmic amplifiers depend on this. Okay. The old saying that IC depends on IB, that's true for some applications, but not for logarithmic amplifiers or differential amplifiers or whatever. The relationship in here, it will be that VBE equals the KT over Q, the natural logarithm of IC over IS. And as we discussed previously, K, of course, is the Boltzmann constant. T is the temperature in Kelvin. Q is the charge of electron. The natural logarithm, IC, is the current, the collector current of a transistor. IS, it has something to do with the manufacturing of that transistor called saturation current, but it has to do with a specific transistor and how it's made. Well, I'm interested in actually that straight line in there. See? We have a linear scale in here for VBE, And you have a logarithmic scale in here for IC. And as you see in here, as you increase VBE linearly, okay, as you increase VBE, IC increases, okay, logarithmically, or as we see in here. Okay, so this is the idea. That straight line, that logarithmic scale, and that linear scale. Okay, so that shows how IC is behaving with respect to VBE. And of course, it shows in here in the equation when you have that natural logarithm in there. Anyway, let's go back to our lecture. Okay, here we are. Now, as we said before, this is the inverting amplifier. And we put an input voltage in here, which has to be positive, by the way. Okay. Putting an input voltage in here on the non-inverting, that will force the op-amp to lower its output voltage. And when it lowers its output voltage, it's going to turn Q1 on. Okay, and a current will start flowing through that transistor from the emitter, okay, all the way to the collector in there, and through the op-amp and that transistor, and then you're going to create your virtual ground in here. And this is a closed loop, by the way. This is a feedback. That's a closed loop. And that point has to be equal to that point, because this is the duty of the op-amp to make sure that that point doesn't go above the ground and doesn't go below ground. That's the duty of the op-amp to handle this. Okay. And whatever that VBE is will be copied by that Q2 in there. And when it's copied in there, it will be amplified by this non-inverting amplifier. Okay, so let's see, when we apply some voltages, what's going to happen. Suppose we applied 1 volt at the input in here. And this is a virtual ground. So that means 1 volt over the 1K, that gives you a 1 milliamp. And that means a 1 milliamp must go through the emitter of that transistor, through the collector tube, to make sure that that point is virtual ground. And that 1 milliamp, of course, that 1 milliamp will increase VBE by a value related to the 1 milliamp. Okay, again, and I said before, maybe when you have that 1 volt, maybe you're going to have about 0.6 volts across VBE. Doesn't really matter. It's 0.6, 0.62, 0.54, whatever, because those are matched. We don't care, actually, what is the starting point for both of these transistors. But this is just an example. Okay. So now, and that's the idea, if we increased the input voltage to 10 volts, that means you're going to have 10 folds of that current. And as we know from the equation before and the graph before, the increasing IC by 10 folds means that VBE has increased by 60 millivolts. Doubling IC means 18 millivolts. Okay, that can be shown on the graph before and from the equation, of course. Equation that VBE that equals KT over Q, the natural logarithm of IC over IS. Okay, so IC will increase, will double. When it doubles, that means you have 18 millivolts increase in VBE. And if you have 10 times that current, 10 folds that current, that means VBE will be increasing by about 60 millivolt. That's just to explain that relationship, which, as we said before, it's always logarithmic. Now, this is at the ground point, that base in there, okay? So that means whatever current is there will create a VBE in here that will be copied by that Q2 in here, okay? And that, of course, will show at this point that little difference in there. So let's say if we double that current, we'll have 18 millivolts. So we're going to get our 18 millivolts in here, okay? Which is a negative 18 millivolts, of course. And if we have 10 times that current for Vn equal 10, so we're going to have in here a minus 60 millivolts. So, we have in here either a resistor or a current source. So once that Vx goes down, because we increase the voltage, because we increase the current, okay, that point in here, which is the non-inverting input of this op-amp, will also go down. A resistor in here or a current source, doesn't really matter. You can move this point up and down based on whatever voltage you got in here. So let's say we increase the current by 10 volts. That means this point went down by about 0.6. Sorry, 60 millivolts, 0.06. Okay, that means 60 millivolts minus 60 millivolts are present at the non-inverting input due to that input voltage of 10 volts. Amplifying that signal with a gain of 16, we have in here 15K divided by the 1K, that's equal 15. And this is a non-inverting, we add 1 to it, which is that voltage across that R2, it becomes 16. And in here, as we see in here, it's minus 1 volts per decade. An increase of that current of a decade will give you minus 1 volt for every decade of the change of the current from 1 milliamp to 10 milliamps. If it went from 1 milliamp to 100, that means you're going to have 2 volts in here, which equals the same equation in here. V equal minus log that Vn. Okay, now we have why it's 16. It actually, the 60 millivolts, you have to multiply it by a number to be equal to about that 1 volt in here. That's why I was saying that you can change the base of that log to whatever you want. And here we have it to the 10th, to the 10 log to the 10, okay? That's why we have it around 16. And we got in here about 960. Actually, it can be a little bit more than that, We assume it's 60 millivolts, maybe it's 62 or 63, whatever, okay? And this can be adjusted. You have to make sure that you have a good operational amplifiers in here, okay, with a low VOS and IOS, to have a good, precise results. And what else we have to talk about? Yeah, the idea in here of making this circuit do the multiplication too. So in order to make the multiplication, okay, as we know in math in here, okay, 2 times 4 equals 8 in here, or the log of 2 plus, note that plus in there means summing, log of 4 will equal the log of 8, okay? The log of 8 will equal about 0.9, okay? And how we do that by our circuit? We simply design the first log circuit, that one in here for an example. We design our another log circuit, duplicate of this one, okay? We make this input number 1, we make this input number 2, okay? And after that, we get the outputs of both of these circuits to a summing amplifier. It has to be a non-inverting summing amplifier where you can add both of these logs in here, okay, to get your final output. So this is the idea of how can you do a multiplication. In a case like this, you simply just did the multiplication, which is 2 volts multiplied by 4, which equals to the 0.9. You want to get a real number of that, you can reinvert it again, put an anti-log for an example. Okay, so you can get your true values for multiplications. You get your 8 volts for sure. So this is the idea. I mean, you know, making linear circuits do mathematical operations. And what do we have in here? We have Vn equals 2, Vo equals 1. Okay, and this is how it's done. How it's done to see how that 0.9 came. Okay. We have a Vn of 2 volts in here, so the output will be minus log the 2. We have a Vn of equal 4 volts in here, and the Vo minus log of 4. And that equals in here 0.29 volts, that's the minus log of 2, and minus 0.6 volts, that's the log of the 4. Add them up together, come up with something like about 0.9 volts that we got in here. Okay. So this is how this circuit works. And here just maybe, yeah, some just derivation on how you get your gain to be equal to 16 volts based on the log of 10. So I believe that's about it. This circuit, by the way, is taken from the Art of Electronics book. If you want more details on the circuit, you can check that book. I have information about it. Okay, well, thank you for watching, and you have a nice day.